This is Math 261. This is section 11.5 on lines and planes in space. And this is part 2. In part 1, we talked about what's called the parametric form of the equation of lines in 3D. So a line in 3D can be described this way. For fixed numbers x1, y1, and z1, which are kind of like a starting point, and direction numbers a, b, and c, we have equation x equals x1 plus at, y equals y1 plus bt, z equals z1 plus ct. So those are parametric form equations. There are also these symmetric equations, which are a different version of the equation of a line in 3D. The statement is made here, you can eliminate the parameter to obtain these symmetric equations. I want to show you what that means and then do the example down below. So if we take the first parametric equation, what I mean is the x equals x1 plus at equation, and if we solve that for t, so x minus x1 equals at, so x minus x1 over a equals t. Now let's leave that b for a moment and go to y equals y1 plus bt. Same thing. It's really literally the same, but you change the x's to y. Y minus y1 over b and change the a to b equals t. And this is probably totally redundant, but I just want to write it out. You see, you can do the same with z equals z1 plus ct. So that will be z minus z1 over c equals t. So x minus x1 over a is equal to t. But t is equal to y minus y1 over b. So x minus x, this should be x minus x1. That over a is equal to t, and t is also equal to y minus y1 over b. And so these two things are equal to each other. But t is also equal to z minus z1 over c. And so these equations are called the symmetric equations of the line. And this is what's meant by eliminating the parameter to obtain them. Now in this example, let's get down to the nitty-gritty of getting an equation of a line, some numbers. In this diagram, we have a point, 1, negative 2, 4. That's giving us x1, y1, and z1 are the coordinates of that point. And then we have a vector, v, 2, 4, negative 1. Remember, those values are the A, B, C values, the so-called direction numbers. The vector is A, B, C. Okay? So this is A equals 2, B equals 4, and C equals negative 4. Okay, now it's pretty much straightforward. The parametric form equations are x equals x1. You know, I'll write them out in general, just so nothing's left to the imagination at all here. That's in general. But now we know it's x equals, for this example, 1 plus 2t. And then the second one, the y1, in general has the same form, y equals y1 plus bt. And in this example, y1 is -2 and b equals 4. So y equals -2 plus 4t. And then for z, in terms of parametric equations, in general, z1 plus ct. And in this problem, z1 is 4, so z equals 4 plus -4t. z1 is 4, c is -4. So the parametric equations are x equals 1 plus 2t, y equals -2 plus 4t, and z equals 4 plus -4t. To get the job done for the symmetric equations, it's kind of the same. They're just of a different form. You see, in general, the symmetric equations look like this. X minus x1 over a equals y minus y1 over b equals z minus z1 over c. So when I say it's kind of the same, what I mean is that you plug in the numbers. You know x1, y1, z1, and a, b, and c. So you're really good to go here. So we have x minus, again, it's all coming back to these, x1, y1, and z1, and abc. So x minus 1 over 2 equals y minus -2 over 4 equals z minus 4 over -4. And just to summarize here, I've tried to make a point with a highlighter in terms of here's the equation for x equals 1 plus 2t. You can see here where the 1 and the 2 go. And similarly, here's the equation for y with a -2 plus 4t. And you can see the -2 and the 4. And those direction numbers are in the denominator. That's going to be useful later on, actually. Z equals 4 plus 4t is the z equation. And you can see where the 4, z minus 4, and the -4 would be c, where they go.